Hi everyone, Dr. J here, and in this video we're going to continue talking about loading and performance for both fixed wing and copter aircraft. As I've mentioned before, the FAA doesn't distinguish between fixed wing and copters, quadcopters for example, in their Part 107 exam, so you'll need to be able to answer questions related to both of them to pass that exam. Just a reminder, here's some of the links to the places of information where I'm pulling the information from for this lecture. So you can check out those links for more details. And as I said, some of the topics for today are really only relevant for fixed wing aircraft, but you're still required to know that information in order to pass the Part 107 exam. Okay, so we're talking about forces acting on the aircraft, loading and performance, and how these different forces are changed by different things that we do. For example, adding a payload or changing the payload on a drone is going to change the weight. It might change the forces acting on the aircraft, and so we have to think about all those things when we're flying different types of aircraft. And this is especially true for fixed-wing aircraft. Thrust on a fixed-wing aircraft is coming from the propeller or the motor, the engines, whereas the lift is coming from the wings. So two different places. On a quadcopter, of course, lift and thrust are both coming from the propellers. So one of the things that we need to do is learn some terminology. And the first one that we're going to learn is angle of attack, or AOA. Angle of attack is, let's look at this diagram here of this aircraft. So our aircraft is moving to the left, straight across the slide. The relative wind is the direction kind of opposite of the aircraft motion. So you see the relative wind direction here, aircraft motion is here, relative wind is the direction the wind is coming compared to the aircraft direction. You'll recall that lift is acting perpendicular to the axis of the aircraft. So lift is not just acting straight vertically, but it's actually acting vertically from the wings, so perpendicular to this axis along the aircraft's body. And then, of course, if we have a propeller here, the thrust is acting in that direction. So again, not straight. The thrust in this case is not acting parallel to the aircraft motion. It's acting at some angle. And that angle between the thrust, kind of the angle here between the thrust of the aircraft and the aircraft motion, is called the angle of attack. You can also think about this as the angle between the wings of the aircraft and the aircraft motion in the case of a fixed-wing aircraft. And this angle of attack is important because, so again, the relative wind is coming from the left-hand side here, straight across the slide, and it's hitting the wings. And so the wings are generating lift, which is acting in this direction. Lift, the vertical component of the lift, is counteracting weight, as you can see here. And then there's going to be some component of the lift, which is actually pulling the aircraft backwards, and that is called the induced drag. Okay, so we sort of understand this diagram now, hopefully, and rewind the video if you need to go back and kind of look at that again. But we've got all these forces acting, and we have this angle of attack now, which is, again, the angle between basically the angle between the wings and the relative wind. And the reason this becomes important is with something called stalling. And stalling is going to occur at a particular angle of attack called the critical angle of attack. And what does stalling do? You can see here on the y-axis of this graph, this is the lift coefficient. So when our when our angle of attack is 15 degrees, which is the stalling angle, the lift coefficient goes from going up to going down. Now, what does that mean? So let's, again, look at our diagram here. So here's a wing. Here's the angle of attack. Basically, again, the angle between the wing itself and the relative wind. And you've got our forces acting there. Now, this lift coefficient is, just think about this as a measure of how much the wing is able to lift the aircraft up. So a lift coefficient which is higher is providing more lift than a lift coefficient which is lower. And if the lift coefficient is too low, then the aircraft won't rise. It won't be able to get off the ground and into the air. On the other hand, if the lift coefficient is very high, let's say we have a lift coefficient up here around 0.8 or 1, that's going to provide a lot of lift to be able to lift the aircraft up off the ground and keep the aircraft from falling to the ground. Now, what do you see is happening at the stall angle? At the stall angle, and again, just think about increasing this angle of attack. So you sort of are slowly increasing the angle of attack, and as you increase that from 0 or so, the lift coefficient increases. So the more the angle of attack, the higher the lift coefficient, until you get to this stalling angle or this critical angle, and then the lift goes down. So by increasing our angle of attack, we can increase the lift that we have to lift our aircraft up into the air. But if we go too high, if that angle of attack becomes too large, we're going to stall, which is lose our lift. So here's a quote from this aviation website. When an aeroplane stalls, this is the British spelling here, when an aeroplane stalls, it is not like a car, so the engine is not stopping. Don't think about the airplane stalling as the engine stopping. The stall is a breakdown of the smooth airflow over the wing into a turbulent airflow, and that results in a decrease in lift. The lift will no longer support the airplane's weight, and the airplane will sink. Now you can imagine if you're flying an aircraft and you all of a sudden lose the ability to keep the aircraft in the air and the aircraft starts to sink, that could be a bad thing, especially if you're flying low to the ground. So this is one of those things which are going to be happening with fixed-wing aircraft and not quadcopters. Quadcopters essentially have no chance of stalling because their thrust and their lift is provided by the same thing, the propellers that are around the aircraft. And the only solution to a stall is to lower the nose of the aircraft. This is actually very important, a very important thing you should note. Will probably show up on the FAA exam. The only solution to stalling is to lower the nose of the aircraft. And why is that? If I back up here, if our angle of attack is too high, that means this angle here is too high. That means the nose of the aircraft is pointed up too high. And we need to lower the nose of the aircraft. That will reduce this angle of attack. That will move us down the chart from a high angle of attack to a lower angle of attack, and that will allow this lift coefficient to come back up. So let's say we start over here at 20 degrees. By lowering the angle of attack, we're able to get back over here to this region. Let's say we lower it to 12 degrees. Our lift coefficient becomes much higher than it was at the 20 degrees. So stalling has to do with the amount of lift that you're generating, and if you start to stall, the thing to do is to lower the nose of the aircraft. Let's talk about another thing which is related, not exactly the same thing. This is the load factor. And a load factor is a result of centrifugal force acting on the aircraft, sometimes referred to as the resultant load. And this is basically the extra gravity or the extra acceleration that you feel when you bank the aircraft or go around a curve. Now, if any of you have been on a roller coaster, you will have experienced this load factor, because a roller coaster is going around these loops and you're twisting and turning, and you'll feel an additional acceleration, which is it feels like an additional gravity. It makes you feel heavier. Same thing if you've been in an elevator. When the elevator starts to move up, you'll feel an additional weight. It feels like you're heavier. And this is actually the same exact thing that results when we bank an aircraft, when we're turning an aircraft, or when it's moving up or down. So in this case here now, we're moving up at an angle. We're not moving straight ahead, but we're actually moving up in elevation, or when we turn sideways and we bank the aircraft. Either of these things result in an increased load factor because of the centrifugal force that is acting on the aircraft. So here we have gravity acting, but now we have this additional centrifugal force, and that results in an overall increase in the gravity that you feel. So this, I don't want to say gravity, but it's the acceleration that you feel, which usually we attribute to gravity. In reality, it's both the gravity acceleration and this centrifugal acceleration. Now, there are some unfortunate stories about this. For example, here is a news article about a pilot . So, for example, here is a news story about a pilot, a baseball player actually, who was flying a private airplane, a propeller plane, the Icon A5, and actually crashed because he was doing some maneuvers, and his maneuvers were such that he actually lost the plane. He actually lost control of the plane, and the plane crashed because the load factor increased to twice regular gravity. And so the angle of attack increased to 15 degrees. So he was at a very high angle of attack. That resulted in stalling. And then the load factor on the aircraft was already greater than gravity. So the airplane was actually both banking and climbing, a climbing right turn. at a particular airspeed. And then during the maneuver, the bank angle of the I-5 increased to more than 50 degrees, and then the pilot lost control of the aircraft and crashed. So let's talk about this a little bit, how this works. So load factor is 0 for straight and level flight, and then increases with bank angle or attitude. So as you increase, you get more banked. The resultant load, the centrifugal force acting, and you can kind of see these things here, the centrifugal force becomes larger as your aircraft is tipped more steeply. Same thing if you're increasing in elevation or decreasing in elevation, same thing applies there. So again, lift is always acting perpendicular to the aircraft's lateral axis and the relative wind. And so when you combine these things together, you have the result that this centrifugal force adds to the weight of the aircraft and gives you this resultant load. And here's the important part. Your vertical component of the lift becomes less as you tip the aircraft more. So you see this total lift here? The vertical component is less where you are more tipped. But the vertical component of the lift must be equal to or greater than the weight at all times. So as you're tipping, you're losing that vertical component of lift. It becomes less and less as the more you tip, but the weight is staying the same. And that has to, you cannot get to the point where the vertical component is less than the weight or the aircraft will fall. There's actually a pretty nice functional form for the load factor in terms of the bank angle. So you can see here as the bank angle increases, there's an exponential increase in the load factor. So for a bank angle up to 30 degrees, there's really not much change in the load factor. So bank angles up to 30 degrees won't result in that much of an increased acceleration. But as you go from 30 to 60 degrees, you increase from about a factor of 1 to about a factor of 2. So at 60 degree bank, you have a two times the acceleration of gravity acting on your aircraft. And above 60 degrees, then it just exponentially increases. So as you increase your airspeed, you also increase your stall speed. So in other words, the slower that you go, the easier it is to stall. The faster that you go, let's say you're over here at 160 miles per hour, you have a pretty wide range of load factors where you're safe, essentially. On the other hand, if you're only flying at 80 miles per hour, there's a very narrow range, a relatively narrow range of load factors before the aircraft starts to stall, before your lift is no longer sufficient to keep the plane up in the air. As the angle of attack changes and as you bank the aircraft, your the amount of lift that you have is decreasing. And so for straight and level flight, it's not a problem, but as you start to bank at low air speeds, then you can very quickly get to the point where you no longer have enough lift to keep the aircraft in the air. And of course, in some part of this graph, then you start to do damage to the aircraft. And so as I say here, abrupt maneuvers at slow speeds can lead to stalling. So you try to bank your aircraft, but you're flying at a very slow speed, then you stall, you lose elevation, and in the case of this unfortunate story with the baseball player, you crash. All right, so we've talked about stalling, we've talked about the load factor and how that affects the stability of your aircraft. Now let's talk about stability specifically, which is the inherent quality of an aircraft to correct for conditions that may disturb its equilibrium and to return to or continue on the original flight path. Well, that is a long definition of stability. Basically, the idea here is that as the aircraft is moving around, you might be flying straight and level, or you might have to turn the aircraft from side to side. You might bank the aircraft. The aircraft might lift its nose up or down. So imagine having a cup, and the bottom of the cup is small and the top of the cup is wide. If that cup is sitting upside down, it's going to be hard to tip that cup over, even if you blow on it or even if you tip it with your finger. The cup is going to tend to return to that wide side. On the other hand, if you have a cup sitting with its narrow side down, then that's going to be unstable. By the way, these words are words that you'll want to know. So rolling the aircraft is side-to-side motion. Yaw is rotation around the vertical axis, perpendicular axis, I should say. And then the elevator, up and down, that's going to be the aircraft's pitch. So pitch, yaw, and roll are going to be three terms that you'll want to remember.